Good morning, everyone. So, welcome to my YouTube channel, Math of the. So, today we are going to see sixth lecture on group automorphism. So, let's start today's session now. So, today we are going to see a theorem. Let sorry the set IG of all inner automorphism of a group G is a normal subgroup of the group of its automorphism isomorphic to the quotient group. Quotient group is also called factor group. G quotient Z of G, where Z is center of G. So what is the statement of theorem? The Ig denotes the set of all the inner automorphism of group G. And this Ig is a normal subgroup of capital AG. Okay, this is the meaning. And this Ig is isomorphic. It means group isomorphic to G upon Z, quotient group, where Z is center of G. Okay, we have to prove this. Okay. So AG denotes, so AG is what? Let AG denote the group of all automorphisms of G. AG denotes the, so AG is group of all the automorphisms. Okay. We know that capital AG is group of all the automorphisms. Okay. All the automorphisms. And we know that capital I is capital I is a set of all the inner automorphisms. Therefore, capital IG is contained in AG because capital AG denotes the group of all the automorphisms and IG denotes the group, IG denotes the all inner automorphism. Inner automorphism is also automorphism. That is why this is containing capital AG. Okay. Now, we prove the following two results. We shall first prove the following two results. What we are going to prove? First, we are going to prove that the inverse of FA is nothing but FA inverse. Okay. Second one, we are going to prove that FA FB is nothing but FBA. Okay. FB. We are going to prove these two results. So first one is, what is first one? So we are going to first prove first one, that FA inverse is FA inverse is equal to FA inverse. How we will prove it? So you take this. What is FA? FA inverse X is equal to FA inverse X. So what is this? What is this? Now open this. What is this? This is nothing but A inverse X. A inverse. So what is this? FA. A inverse is A. A. Now what is this? You consider this as an element. You will get A inverse. You open this. Okay. So what is this? This is AX, A inverse A. Okay. Now you can use associative property here. So what you will get? A inverse A, X, A inverse A. Okay. So what this is E identity, this is identity. So this is X. So this implies F A inverse X is X. For all X belongs to G. Okay. But this is nothing but property of identity map, identity, automorphism, inner. So this implies FA inverse is I. Similarly, we can show that FA inverse FA is identity. So we have FA inverse I is equal to FA inverse FA. So what does it mean? So the product FA and FA inverse are in AG. Okay. So their product is, it means after operating these two elements, we are getting identity elements. So what does it mean? It means the inverse of FA element is nothing but FA inverse. Okay. So we got this. Now we are going to prove second one. FA FB is equal to FBA. How we will prove it? So FA FB, you take X from G. What is this? FA FBX. So how to write this? This is nothing but B inverse XB. Now open this. What is this? A inverse B inverse XB. Now I can combine these two. Okay. I can combine these two. Now what is this? A inverse B inverse can be written as A BA inverse. Okay. So this is what? This is FBA X. So this implies FA FB X is equal to FBA X for all X belongs to G. So this implies FA FB is equal to FBA. So it is proved. Okay. So this is proved now. Okay. Now we are going to prove that now IG is subgroup of A2. How to prove it? To take, let FA FB, FA and FB, we are taking two elements. Let FA FB belongs to IG. Okay. We are taking two elements, FA and FB. Sorry. First of all, we have to show that IG is non-empty. Okay. First of all, we have to show that I is non-empty. So IG is non-empty because because identity always belongs to G. Then F E is nothing but identity map, and that will belongs to IG. Okay. Because FE will be identity map, and that will belongs to IG. Because FEX, what is this? This is nothing but E inverse XE. But inverse of the identity is identity, that is X, that is IX. Or all X belongs to G. So this implies F is nothing but identity map. So identity map will always belongs to IG. So this implies IG is non-empty. Okay. Now next, let FA and FB. We are taking two elements, FA and FB belongs to IG. Okay. Then what is FA, FB inverse? What is this? This is nothing but FB inverse will be what? FB inverse. Okay. Now solve it. So what will be this? By second, we have proved that FB inverse by part 1. By part 1, you take any element, the inverse of FB. FA inverse is nothing but FA inverse. So we are taking B in place of A. So by this one, what we will have? By this one, what we will have? We'll have FB inverse is FB inverse, and FA into FB is FBA. Okay, we will use these two properties here, which have shown earlier. So now what is this? This is nothing but FB inverse A. Okay. Now G is group. G is group. A, B belongs to G implies B inverse A belongs to G. Okay. So this implies this belongs to IG. Because the element of this form, F in base, the element of G. B inverse is element of G, that is why this is belonging to base. So this implies FA, FB belongs to IG, implies FA, FB inverse belongs to IG. So this implies IG is subgroup of A's. Okay. So we have shown that IG is a subgroup of AG. But in theorem it is given that it is a normal subgroup. We have to show that this is a normal subgroup. Okay. We have to show this is a normal subgroup. Okay. So we have shown that this is a subgroup, but we have to show that this is a normal subgroup. So till now we have shown that this is a subgroup. So now we will show that this is a normal subgroup. IG is normal subgroup of AG. Okay. So we have shown that this is a subgroup. Now we will show this is a normal subgroup. For normal subgroup, we will take element. Now let F belongs to AG. Okay. Then F inverse F A F. What will be this map? This is nothing but F inverse to take this one. What is this? F inverse. What is it? A inverse F X A. Okay. But so I will take inverse there. Okay, no problem. Okay. So this is inverse. Okay. Now F is homomorphism. F is automorphism. So it is F is homomorphism. Okay. So we will use that property of homomorphism. Okay. So F A inverse F inverse. But we are operating F with its inverse. So this is identity element. It will be identity map. So this will be identity map. Okay. So what is this? This is I X F F and homomorphism takes inverse of the element to image inverse. So this will be FA inverse will be FA inverse and this is X F. Okay. So what is this? This can be written as F in base F A X. Okay. Since F is G to G, so FA belongs to G. So what does it mean? It means that so F A F inverse X is equal to F A X for all X belongs to G. So this implies F A F inverse F A. But F A is element of G, so this belongs to IG because the base element belongs to G. Okay. So this implies okay. Since IC is subgroup of AC and F AF inverse belongs to IG for all FA belongs to IG and F belongs to AG. So we conclude that IG is normal subgroup of AG. Okay, so this is done. IJ is normal subgroup of AG. Okay, now we will prove remaining part of this theorem. Okay. Now we have to show that IG is isomorphic to G upon Z. It means symbolically, what is the meaning of this? IG is group isomorphic to G upon G quotient Z. We have to show this. Okay. Okay. Now we are defining a map phi. Consider the mapping phi G to IG defined by phi A is equal to phi A is equal to F A inverse for all A belongs to G. So we have to show that this is homomorphism. This is homomorphism and onto. So phi is homomorphism. Phi is homomorphism. Let A and B belongs to G. Then A and B belongs to G. Then what is phi AB? Phi AB is equal to F AB inverse. Okay, this is equal to F B inverse A inverse. But we can write this. It will be changed. Once we open this, it will be A inverse F B inverse. Okay, we have shown in part 2. Okay, we have shown 2 parts in starting 1 and 2. By that we have this one. Okay, what is this? This is phi A and this is phi B. So we have phi A B is equal to phi A phi B for all A B belongs to G. So this implies phi is homomorphic. So this implies phi is group homomorphism. You can say homomorphism or group form. Same thing because we are studying groups. And phi, next we proving phi is onto. Phi is onto. Phi is onto. Let Fa belongs to Ig. Okay. Then A belongs to G implies A inverse will also belongs to G. We have phi A inverse is equal to F A inverse inverse. That is nothing but Fa. Therefore, P1 any Fk belongs to Ig. There exists element A inverse belongs to G such that phi A inverse is equal to Fk. So we conclude that phi is onto man. Phi is onto. Now we have now phi G to Ig is onto group homomorphism. By first fundamental theorem of groups. We have, if you have a homomorphism that is onto, then you take quotient of that group by kernel, that will be isomorphic to image of the group. Okay. So this is equal to by fundamental theorem of groups. What we have, first fundamental theorem of groups, of homomorphism of groups. We have that phi will be, what is fundamental theorem of group? I am writing here. Phi, if you have a map G1 to G2, homomorphism onto then G1 upon kernel of phi is isomorphic to G2. This is first fundamental theorem. Okay. So here this map is onto G is a group and I is also group. So by fundamental theorem, G quotient kernel of phi, that is isomorphic to I. Okay. Now if we can show that kernel is that kernel of phi is nothing but Z center, then we are done. We will put in place, we will put Z in place of phi. Then let's say it's 1. Now, what is the kernel of phi? Kernel of phi is nothing but kernel of phi is nothing but Z belongs to G such that phi Z is equal to identity in IG. What is identity in capital IG? That is I. What does it mean? It means Z belongs to G. What is the meaning of this? This is meaning of this is F Z inverse in identity. And what is this? It means F Z inverse X is equal to I X, for all X belongs to G. So this is Z belongs to G such that Z inverse X Z is equal to I axis will be I X, for all X belongs to G. Okay. Now what is this? Z belongs to G such that Z inverse Z is Z. So Z, sorry, one. So I start with Z belongs to G such that this is identity and this is Z inverse. So this is okay, 1. Yeah, there will be Z inverse. Okay. So this is equal to Z, the inverse of Z. Z inverse will be Z. This is Z inverse is equal to X, for all X belongs to G. Now I can operate Z inverse from the right. So what I will get? This will be equal to X Z. So what is this? What is this? You collect all the elements of G which commutes all the elements of G. Such set is called center of G. So it means kernel of this implies kernel of phi is equal to Z. So from 1 and 2, we have what we have. In place of kernel, you put Z. So G upon, we have this one from equation 1, that was isomorphic to IG. But we found that kernel is nothing but center, Z. So from equation 2, what we have, we will put this here, G upon Z is isomorphic to. Okay. So we have this one. So we are done. Okay. So this is done. 1 minute only. we have shown that Ig is isomorphic to G upon Z. I can write it in this way also. Ig, same thing it is. I'm writing it on the right side, left side, Ig. Okay. Therefore, hence, Ig is isomorphic to Ig is isomorphic to isomorphic means group isomorphic. Isomorphic to G quotient Z. Z is center. Okay. So this is done. So theorem is proved. Okay. If you have any problem related to this lecture, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much.